Well, good afternoon, everyone. I'm Alan Taub, Director of the University of Michigan Electric Vehicle Center, and glad to see that you are joining our fifth in our surge session webinars. By the way, if you missed the first four, they are recorded and accessible through our website. And just as some background for those of you who are new to the EVC, we were established in late 2023 with a $130 million investment by the state of Michigan. And our goal is to drive innovation, education, and workforce advancements as we help companies in the state of Michigan to get through the transition from internal combustion engine to battery electric vehicles. It's my absolute pleasure to
Hello?
introduce our speaker today. Uh, if you can put everybody on mute, please, Ellen, except me and Neil. Um, Professor Neil Dasgupta is a member of mechanical engineering and material science and engineering at the University of Michigan. Very well known in the field, a pioneer, an acknowledged expert. He actually also serves within the Electric Vehicle Center as our battery technology lead, and he's the CTO and co-founder of Arbor Batteries Incorporated, a startup focused on commercializing fast-charging battery technologies. I always learn something when I listen to Neil, and I'm looking forward to his presentation today. With that, a reminder, please hold your questions until the end. Jamie Ratcliffe, our communications director, will handle your inputs through chat, but you can put them into chat during the session. With that, I'm handing it off to Neil.
Hey, thanks so much, Alan. Let's see, let me go ahead and share my screen here. Hey, how does that look? Good?
That looks good,
Okay,
thanks.
great. Well, thanks so much for the invitation opportunity to present here. I'll be talking about some of our work we've been performing over the last 6 years or so, focused on very fast speed charging of lithium-ion batteries, which many of us know is one of the key bottlenecks to consumer acceptance of EVs. All right, so just let me kick off with a little bit of a motivation. Here's a figure that many of us are familiar with, the experience of being at a gas station and refueling the vehicle, which takes on average on the order of 3 to 5 minutes. On the other hand, when we think about recharging our batteries in our electric cars, even for aggressive so-called supercharging of the vehicle, you're talking about at least a half an hour, and that's not to go from 0 to 100% charge in the battery. So we're still talking about a factor of 10 difference in terms of the time to recharge as opposed to refuel, which can really play into people's reluctance to make the switch to an electric vehicle. And how important is fast charging? Let me just present a little bit of a thought exercise here. So imagine we were going to take a road trip in our electric car here from Ann Arbor to the Washington, D.C. area. And we had two different car options. One of them was a short range car, so it had a smaller battery pack, but this battery allowed us to recharge fully in 15 minutes. Consider option of car 2, where you could go a further range per charge, but you had to wait 1 hour to recharge the vehicle. What we would see is that with car 1, we would need to make 3 charging stops along our road trip, whereas with car 2, we don't need to make 1 charging stop. But because of the fact that we had to wait an hour with car 2 as opposed to waiting 15 minutes, the net time of the trip is actually longer for car 2 versus car 1. So fast charging ability is really a critical sort of barrier for EV adoption to help overcome the range anxiety and convenience concerns with making the switch to an electric vehicle. Now, one of the interesting things is that consumers of cars, when we're going to make a purchasing decision, are actually making purchasing decisions on relatively rare events. So this plot shows just statistics in terms of the average trip in a vehicle in the United States by trip distance. And what we see is that something like 60% of the trips are actually less than 6 miles in distance. And almost all of them are less than 30 miles in distance. On the other hand, we see consumer demand for electric vehicles that can drive 300, 400-mile ranges. So consumers are making decisions on these less than 5% scenarios in terms of their usage. And actually, when we started performing this, research on fast charging of batteries, we started actually asking the question, how much do people actually value their time in the first place? And you can see how that would be a critical thing for the engineering of fast charging batteries, because we would have to determine how much money are people willing to spend to save time in terms of the ability to charge faster. As I dug into the literature, I found actually an interesting study from the 1980s in an economics journal, where it turns out in 1980s in the state of California, Chevron gas stations were required to pay lower, taxes than other gas stations, and as a result, you had this really interesting situation where the gas on one side of the street was 15 to 20 cents cheaper per gallon, and that's in 1980 dollars, compared to the gas on the other side of the street. So as you can imagine, there were long lines of people lining up to refuel their car in the cheaper gas station across the street as opposed to the more expensive one across the other side of the street. But still, some people were willing to go to the other more expensive gas station because the fact that the lines were shorter. And this is a really beautiful situation for the behavioral economics economists, because they could then interview people at both gas stations and ask the question, who was willing to pay more to have less time waiting in line to refuel their vehicle, right? And so that's kind of analogous to the demand for fast charging for electric vehicles at charging stations. And the interesting outcome of this was that for most income levels, the estimate of the value of time spent waiting at the gas pump are very similar to the after-tax wage rates of the respondents. So in other words, people that make more money are willing to pay more money to save time at the gas station, and people that make less hourly rate are willing to wait longer to save money on the refueling. So you can already see that this fast charging demand for the electric vehicles has implications not only in terms of the convenience and the sort of acceptance and the range anxiety, but also plays in some of the economic aspects of who's going to be able to afford to buy an electric car and afford to wait a certain amount of time to recharge. And interestingly, also, if you look at today's electric vehicles, consumers are oftentimes making decisions on different versions of the car that they might buy. So you might buy a standard range car that costs you, say, $38,000, and you could pay to increase that range from 263 miles to 353 miles, but that's going to charge you about $9,000 more for that bigger battery pack. Now, if you think about that last slide of people, how much they value time based on their hourly wage, the median hourly wage in the US is on the order of $21, $22. So what that means is the people that are willing to pay $9,000 more for the longer range vehicle, right, based on that median hourly wage, should be willing to wait at least 423 hours extra of recharging time over the lifetime of the vehicle to justify the added time. On the other hand, that consumer could also choose to go buy a gasoline vehicle that they could refuel in 3 to 5 minutes. And so simply, many people cannot afford to buy an electric vehicle, not only because of the sticker price of it, but because of the time and the added cost of the time waiting for the recharging. So I really believe that fast charging is an enabling barrier for electric vehicles, both in terms of the range anxiety and consumer acceptance, as well as the economics and the affordability of being a driver of one of these vehicles. And as researchers in the battery space for a long time, in all electrochemical systems, we oftentimes think about engineering systems that deal with the inherent trade-off of power versus energy. And that's what you're seeing on this graph, various different battery technologies over the years, whether you're talking about a lead acid battery or a lithium-ion battery. And we see for pretty much all electrochemical systems, there are these trade-offs where I could design a battery with higher energy density on the x-axis, which equates to a longer driving range if I'm an EV driver. But that may come at the compromise of the fact that now it takes me longer to recharge the vehicle. My specific power goes down. Conversely, I could design a battery that charges very rapidly, but that comes at the cost or the compromise of having lower specific energy and therefore lower driving range. On the other hand, again, we're used to being able to buy a gasoline vehicle where I can refuel 400-mile range in 3 to 5 minutes. So the gasoline customer for the IC engine isn't having to make that kind of trade-off decision in terms of refueling power versus range in the vehicle. So let's dig a little bit deeper into the origins of why does this trade-off exist? Why is it that you can design a battery that can charge fast, but it means you sacrifice range or vice versa? What you're seeing here is a cartoon on the left. It's a snapshot of the inside of a lithium-ion battery. There are three main components. You have your negative electrode, which is what we call the anode. your positive electrode, we can have the cathode, and then in between them is the electrolyte. And the job of the electrolyte is to shuttle the ions from one side of the battery to the other. You can see on the right-hand side a cross-sectional X-ray CT scan, just like in biomedical imaging, you can take CT images of the human body. And with the CT imaging, we can see these layers of material inside the battery. Each one of those sides, the anode and cathode, is typically comprised of particles of a solid material. So on the positive electrode side, this is a metal oxide material like nickel, cobalt, manganese oxide. And on the anode side, the state-of-the-art material is graphite. Graphite, is an earth-abundant, low-cost material that has a lot of favorable properties for batteries in terms of energy density. But as I'll show you in a moment, graphite really has some bottlenecks and challenges that really ultimately limit the ability to fast charge this battery. So as I mentioned, just summarizing so far, the ability to refuel quickly or fast charge remains one of the largest barriers for consumer acceptance of electric vehicles. And for widespread EV adoption, our goal is to be able to enable fast charging without sacrificing energy density. I want to make a car that I can recharge in 10 minutes, but can still drive 300, 400 miles on one charge of range. So far, I would argue over the last 20 years, in terms of lithium-ion battery research for transportation and electric vehicle applications, most of the focus has been on the energy density side of things, right? 20 years ago, you couldn't buy an electric car that gave you 400 miles range, at least not an affordable one. And many of the advances in terms of energy density over the last 20 years have not been, oh, we found some brand new material to replace the graphite in the battery, although we are increasingly starting to see more new materials be implemented in specific percentages into it. But from a manufacturing standpoint, the strategy to increase energy density was to make those particle electrodes thicker. So the current trend is I want to make the particles of my electrode as thick as possible. And that means I have less wasted mass and volume from those inactive components in my battery, like the metal current collectors, the polymeric separators in general. But this is one of the things that inherently results in this trade-off, because as we go to thicker and thicker electrodes, while that increases the energy density, as we can see on the right-hand side, this graph of energy density versus the anode thickness, what happens is the ability to move lithium ions in and out of these thick electrodes becomes increasingly challenging. And that's what you're seeing on the left-hand side. You form these concentration gradients in the electrode that really prevent fast charging from being possible. And this is something the US Department of Energy realized is a major issue. And so over the last 5 to 7 years, there's been a lot of investment in trying to understand the limitations of fast charging and overcome it with various different solutions. What I'm showing here was an early study out of Argonne National Lab where they manufactured these lithium-ion pouch cells. So what you're seeing here on this photograph are these 3 different graphite anodes after a battery was fast charged, and they open it up and take a look inside and take photographs. And what you see is on the surface of this graphite anode, which is normally just this dark black color, you can see that you have this lithium plating, this metallic shiny lithium that occurs on the surface. Lithium plating is an undesirable side reaction of fast charging of graphite, and this leads to a lot of the irreversible behavior. And you can see that irreversibility here when you try to charge these batteries at what we call a 6C rate. So if you're not familiar with C rate in batteries, the higher the C rate, the faster you're charging the battery. So a 6C rate corresponds to a 10-minute recharging time. What we see is whether or not the loading of graphite was low of 1.5 milliamp hours per centimeter squared or all the way high up to 5, all of these quickly converge to about 1.5 milliamp hours per centimeter squared after I try to fast charge it. And what that tells you is that's kind of the fundamental bottleneck of how thick of a normal graphite, and I'm going to talk a lot today about not normal ways of modifying the graphite to overcome this, but your sort of normal state-of-the-art graphite electrode, it's difficult to do this 10-minute fast charging with an electrode thickness that's greater than about 1.5 milliamp hours per centimeter squared. And what that means is I can make a thin electrode that can charge fast, but I'm going to sacrifice that range. So really, we need new approaches to understand and eliminate this lithium plating to achieve fast charging while still enabling these thick electrodes. So let's take a little bit of a closer look inside of this graphite material. What I'm showing here is a cross-sectional optical microscope image of the graphite electrode after we've fast charged it from our battery. And you can see on the top surface this metallic lithium plating that was that undesirable side reaction. And notice underneath you see this color gradient. You see these gold colored particles near the top surface that transition to red, to blue, to gray near the bottom. And it turns out graphite has this amazing property that it changes color as a function of the state of charge of the particle. So the graphite starts out sort of like a grayish black color. And as we start to add more and more lithium in as we charge it, it transitions from gray to blue to red to gold. And so because we're looking at this cross section, we can see that not only do we have this lithium plating at the top surface, but the reason for that is I quickly was able to charge the top surface of my graphite electrode, but those graphite particles in the subsurface region underneath the surface are dramatically underutilized. I'm not able to put the lithium in deeper into the electrode when I undergo these fast charging conditions. So because of the fact that graphite changes color as a function of state of charge, that now for us as scientists made us think, could we use that property to try to image and visualize where the lithium is going during these fast charging operations? And can we develop some baseline scientific knowledge of what the real bottlenecks are to fast charging so that when we put our engineering hat back on and say, I'm going to solve this problem, we can really utilize inference and insights from that investigation. And this is where our group over the last 12 years has really developed and pioneered an approach we call operando video microscopy. And what that really means is we're able to look inside the battery with this optical microscope as it's charging and create these high resolution video images to see what's going on inside the battery. And importantly, we're able to time synchronize that with the electrochemical response, with the voltage, current, and time response. And in a normal battery that doesn't have a window, you can't see inside, all we can really see are things like voltage, current, time, etc. But by synchronizing the video with the electrochemistry, we can identify these signatures of what's really going on. So let me show an early example of that. So this is a paper that's almost 10 years old now from my group, where we first introduced this concept of visualizing what's happening inside the battery and synchronizing it with the voltage. So on the left, you're seeing a lithium metal anode inside of a battery, and on the right, you're seeing voltage versus time. And as I play the video, you can see we're able to observe these dendrites, these non-planar, non-ideal plated lithium geometries that are evolving in time. And on the right-hand side, we can synchronize that with the voltage trace of the material. And this allows us to, again, understand the origins of some of these electrochemical signatures. Now, of course, we weren't the first people to ever come up with the idea of doing optical imaging of a battery as it operates. I want to give a shout out to Steve Harris, a pioneer in this space as well, former researcher at GM, who's now at LBNL. He was one of the first to really observe for graphite, our typical negative electrode material in the battery, how this sort of state of charge evolves over the surface of the material as it charges. So I'll play a video here where you can see this color gradient moving from the bottom to the top of the screen. And this allowed us to visualize diffusion and the mass transport of lithium into and out of the electrode material. And a lot of fundamental insights were actually derived just by observing this video in real time. But one of the limitations of this work is that the visualization is actually happening in the plane of the electrode. The ions are not moving in the same direction as they would inside of the real battery. So to overcome that, our group actually spent a couple years designing a lot of different types of optical visualization cells that allow access of the microscope to look from different angles in different directions onto the surface. And while I don't have time to get into all of the engineering details of those, I can point you towards this ACS Energy Letters paper from our group a few years ago, where we developed what we call this plan view optical visualization cell that lets us look over the surface of the battery electrode and has much more of a uniform in-plane gradient in state of charge, so that now the electric field is really pointing in the direction we want it to. And so that lets us make videos like the one I'm showing on the next slide here, where now we're taking a look at a graphite electrode. This is an electrode, by the way, that was manufactured in the Battery Lab, our unique manufacturing facility here at University of Michigan that's been really enabling for us to do a lot of this research. And on the left-hand side, you're seeing the time synchronization of that with these voltage traces of graphite. And when we slow charge the graphite, when we don't do this at a fast rate, I'll start to play the video, we can see that we're able to measure the voltage of the graphite anode as a function of state of charge, and we see the color starting to change on the right-hand side. Again, those particles are changing from gray to blue to black to gold. Now that we've eliminated that in-plane gradient, you see all of the particles basically change color at approximately the same time. So if I move back and forth, you can see we have a very uniform lithiation of the graphite electrode under this slow charging condition. And in fact, because of the fact that color represents a proxy for state of charge, we can now use the red, green, blue, right, information from our RGB camera to actually understand what is the state of charge locally of each one of these particles as we charge it from 0% to 100%. So now let me show a video of what happens under fast charging conditions. Here right away, even before I play the video, if you look at the left-hand side, you can see the voltage trace looks very different for fast charging than slow charging. Whereas the slow charging had these three very distinct plateaus that come from the thermodynamics of graphite. When we have fast charging conditions, we see the voltage of the graphite quickly drops below zero on the y-axis and then reaches a local minimum and then reaches a plateau. And as I play the video, what you'll see is that the color change in the graphite looks very different under fast charging conditions. We can see that not all the particles turn gold at the same time. Some of them start to lithiate much faster than others. And we can also start to visualize this deleterious lithium plating event that occurs onto the surface. So if I flip back, you can see one of my favorite pictures we've ever taken in our optical microscope. This picture right here reminds me of like a calico cat fur, where you can see some of the particles have already reached this gold state very quickly. Others are still in the red versus blue versus gray. So in summary, what we see is when you go to fast charging conditions, spatial inhomogeneity becomes a big challenge. What used to not be a big difference between a slightly bigger or slightly smaller particle or slightly faster or slower one, you could get away with that at slow rates. But under fast charging conditions, what ends up happening is some of them lithiate much faster than others. And this actually makes us start to think about this concept of synchronicity in electrochemistry. So just like the synchronized swimming in the Olympics, you see people practice so hard to be able to move all at the same time. If we look at our Butler-Volmer expression from electrochemistry, the current density, which is what increases when you charge fast, has this relationship with overpotential. And normally we think of these as singular scalar quantities, right? Like there's a number for current density and a number for overpotential. But in reality, what we see is when we go to these fast charging conditions, some particles have a lower overpotential, other particles have a higher overpotential, and so some of them lithiate and charge much faster than others. And we're able to use this optical imaging to correlate the locations of where lithium plating nucleates and grows as a function of that spatial inhomogeneity. So in summary, this cartoon kind of sums that up. In this graphite electrode, you're applying a net amount of current. If you're applying a slow amount of current, all of the graphite particles sort of lithiate at the same time, at the same rate. As I start to apply a higher and higher current, I see there's more inhomogeneity. Some particles lithiate faster than others, and this creates a lot of the problems of where lithium plating nucleates and starts to grow. So we spent a few years kind of really understanding how does graphite work, what are the origins of this lithium plating, and how do we identify electrochemical signatures of understanding and diagnosing that. But let me now put the engineering hat back on and say, what are some of the solutions to enable or improve the charging rate of these graphite electrodes? And here again, the tenets of electrochemistry, thermodynamics, which is kind of equilibrium, steady state behavior, kinetics, which is really the rate-dependent phenomena. It really changes on how fast or slow the electrochemical process is occurring, or transport. How easy is it to move ions across a membrane or into or out of an electrode? I'm going to show three examples that really think from the thermodynamics, kinetics, and transport perspective, and show you how each one of these knobs are knobs that we can tune as a design engineer to really overcome and improve the bottlenecks to fast charging. So let me start with transport, because mass transport is one of the obvious ones, right? As I showed you earlier, that cross-sectional image, when you try to charge the battery too fast, it's just difficult to get the lithium in and out. You over-lithiate the top surface, you have this lithium plating that occurs, and you didn't really take advantage of a lot of that graphite deeper in the electrode. So here our strategy was, could we introduce channels that allow for very rapid diffusion or transport of lithium deeper into these thick electrodes? And could we do this in a manner that doesn't sacrifice energy density? So this was really the basis of this US DOE project that was funded here at University of Michigan from about 2019 to 2022. This work that I'm going to be showing is in close collaboration with Jeff Sakamoto and Katsuyo Thornton, as well as Jody Mazumdar, who helped us develop a lot of the laser patterning processes. And the idea was relatively simple. We take our standard manufacturing process of making this graphite electrode. Normally, as shown in this middle cartoon, we have this tortuous pathway that really limits the ability to quickly diffuse the lithium ions deep into the electrode. And if we use a laser to literally drill holes inside the graphite electrode, these can create channels for very rapid ionic transport, and this will improve that synchronicity. This will improve the sort of uniformity of the rate of the charging between the particles, and that should, in principle, enable us to charge the battery faster. Importantly, we were also kind of thinking right up front about manufacturing. We didn't want to recreate the wheel on making a whole new type of battery or have to substitute a new material in. This is compatible with lithium-ion manufacturing. This happens after the calendaring step. So it's really just one more additional step at the end of the assembly line. And as long as you can do that fast, which I'll come back to in a little bit later in the talk, you can really do this without being too disruptive of your manufacturing flow. So again, here are some SEM electron microscope images of these graphite particles we manufacture in the battery lab at University of Michigan. I'm showing here electrode loadings of 3.2 milliamp hours per centimeter squared. These are standard porosities and thicknesses for reasonably high energy density lithium-ion batteries. And then you can see the picture of what happens after we've drilled the hole with the laser. We create these beautiful hexagonal arrays of holes, and these are channels, as you can see in the bottom right, with the cross-section that go all the way through the thickness of the electrode. And we can image this sort of cross-sectional profile to see that indeed we have been able to successfully create these holes. HOLE is an acronym we also use, highly ordered laser pattern electrode, that can facilitate this improved ion transport. I want to also mention that throughout the rest of my talk, all of the data I'm going to be showing to you are on industrially relevant pouch cells. So these aren't just small coin cell batteries made in a glove box manually by a graduate student. Here we're really, again, leveraging the battery lab facilities. So we're making multi-layer, multi-amp hour pouch cells. We're utilizing commercially relevant electrolytes, carbonate electrolytes, EC, And so there's not really some magic of we had some different type of material, different type of electrolyte. We want to ensure this is all in technologically relevant formats. And one of the first things we needed to show was that the act of doing this laser patterning doesn't really hurt the battery, right? Because obviously we don't want to make that trade-off. And what we see is that if we just do a standard 1C charge discharge profile, the control anode and hole electrode give essentially the same behavior. But we see dramatic differences when we start moving to these fast charging conditions. If you take that unpatterned electrode and do 4C fast charging, meaning a 15-minute recharging time, you see that after 100 cycles, we've already lost 30% of the capacity of the battery. That would be totally unacceptable to an EV customer. And in fact, even as you can see in the bottom in our coulombic efficiency, which is how much charge we get back compared to how much charge we put in, even within the first 10 or 20 cycles, we're really damaging and degrading the battery a lot. Remarkably, when we look at the whole electrode, what we can see is that we were able to eliminate a lot of those losses in the early fast charging cycles, and we're able to maintain over 97% of the accessible capacity after 100 4C fast charge cycles. The differences are even more dramatic if you push the battery harder to a 6C rate, which again is a 10-minute recharging time. You can see at 6C, the control electrodes lose 40% of their accessible capacity, whereas the whole electrodes still maintain over 93%, with no evidence of this dip in coulombic efficiency, which indicates lithium plating. We then take the batteries, we tear them apart, and we look inside. And what we can see is that the control anode, as I showed before, has a lot of this lithium plating all over the surface. The entire surface of the electrode is covered with plated lithium, and you can see in the cross-section this kind of thick, mossy lithium layer that has plated on the surface. On the other hand, after the whole patterning, what you can see is that we've eliminated lithium plating even after multiple, this is after hundreds of cycles of 6C fast charging. We can see that the whole structure remains intact, and we're able to really charge and discharge this battery at a fast rate without that lithium plating occurring. Now here is a little bit more into the weeds, so if you're not an electrochemist, that's okay. This might be a little bit beyond what you're interested in. But if you are, if you just look at the voltage versus state of charge curves right here, what we can see is that for the control and the pattern cells, they're essentially the same, which again is a good thing. We don't want to degrade our battery at slow charging rate. But under the fast charging conditions, we see the cell polarization, the excess voltage that is required to charge it at this fast rate, becomes more and more significant at 4C versus 6C charging. And we can see after extended cycling of 100 4C or 6C charges, we see a lot of voltage fade. We see a lot of power fade in our cell where the voltage is increasing very rapidly after 20, 30, 50 fast charge cycles in the control, whereas we see a very stable voltage profile after hundreds of 6C fast charging cycles when we've introduced this whole pattern. We also in our group have been developing a lot of unique diagnostic probes. So one of the ones we really like a lot is utilizing a 3-electrode setup. So we're able to insert these micro reference electrodes into our pouch cells that allows us to decouple the voltage trace from the positive and negative sides of the battery. That's what you're seeing on the right-hand plot here. We can see independently under fast charge conditions what's the potential of the cathode versus the anode. And we're able to take the derivative of this. So we do incremental capacity analysis. This is something that is used a lot in battery battery diagnostics, battery controls analysis. We can see here that in the control unpatterned cell, we see a lot of changes in this DQ-DV spectrum. Again, I don't have time to go into all the details here, but I can point you toward this paper we published in Journal Power Sources that really breaks down the interpretation of the DQ-DV spectrum for batteries under fast charge conditions using 3 electrode measurements. And what we see is with the whole pattern cell, we don't see the evidence of this peak that occurs associated with lithium plating. There's a lot of implications for this slide that I wasn't able to go deep on in terms of battery controls and battery management systems and understanding plating in terms of fast charging that you can learn more about if you check out that paper. But finally, let me go back to the target. So the US Department of Energy set this goal and said, we would like you to be able to do at least 500 fast charging cycles. Remember, most EV consumers are not going to fast charge every single time. You're really only going to the fast charger for every charge, maybe if you live in an apartment and can't plug in to your house, right? And even if you are, doing fast charging more often, you'd have to do that quite a bit to hit 500 or 1,000 recharge cycles. So the DOE target was they would like to enable 500 fast charge cycles with less than 20% capacity fade. What we see is that with our whole electrode pattern, we can maintain 93% accessible capacity after 500 4C fast charge cycles, which is a really aggressive charging condition. That's much faster than going to a supercharger right now to recharge your battery in 30 to 40 minutes. And even at 6C, which is a 10-minute recharge, we're able to beat the DOE target. We're also able to exceed the targets of the US ABC. So the US ABC has a slightly different metric, which talks about the delta SOC swing, right? How fast can you take to change it from, say, 10 to 90% or 20 to 100% state of charge? And this is where you see a lot of claims of fast charging batteries. Be cautious, because a lot of claims of fast charging battery will say, I can charge my battery in 15 minutes, but they're only talking about charging from 20 to 80% state of charge. What we see is that with this whole electrode, we can go from 0 to 92% state of charge in 15 minutes and 0 to 90% state of charge in 10 minutes. And not only can we do that, but we can maintain very high delta SOC swings even after 500, 600 fast charge cycles. So we're able to really achieve that dream of fast charging without sacrificing energy density or the range enabled by recharging our battery. So that's one approach. The second approach we took was more putting our thermodynamics lens on. So here we said from a material science standpoint, graphite has some limitations. Are there other materials we could start to blend into the graphite electrode to improve its fast charge capability? Here we look back at an old material that was studied back in the 1980s quite heavily, hard carbon, right? This is actually a byproduct of the petrochemical, refining industry, right? It's a pretty low cost carbonaceous material. It was discarded back a long time ago as a lithium-ion anode material because while it can actually enable faster charging, it has this sort of Achilles heel of having a low first cycle Coulombic efficiency. What that means is that you make the battery with hard carbon, the very first time the battery manufacturer charges and discharges it, it's lost 25% of the capacity of the battery. That's obviously not a desirable thing. Graphite is the one we eventually settled on that has a much higher initial Coulombic efficiency, but suffers from lower charging rate. So we asked the question, what happens as we start to blend these different types of carbonaceous materials together? So again, we went to the battery lab, mixed and blended hard carbon and graphite electrodes. Again, these are all slurry casted and tested in multi-layer pouch cells. And what we can see is that while the graphite changes color, as I showed you earlier, to gold, the hard carbon does not. So you can see now in these fully charged electrodes, the gold particles are the graphite, the non-gold particles are the hard carbon. We can see the sort of rate and independent charging of these different particles. And while there's a lot of information at the top that I won't go into the detail on in terms of the voltage trace, we saw some very interesting trends in the shape of the voltage versus state of charge with respect to blending this hard carbon in. But let me cut to the chase of the end result here. So what we see is that if you have 0% graphite, 100% hard carbon in your electrode, you lose, as I said, about 25% of the capacity in the first charge cycle. If you look at the other end of this graph, if you have 100% graphite and 0% hard carbon, notice we're still losing about 15% of the accessible capacity after the first formation cycle. This is a well-known limitation of NMC cathode materials and batteries, that they lose their sort of reversible accessible capacity due to these structural changes in the first charge cycle. What that means, however, is that if I blend in, notice I go from 0% to 25 to 50, if I blend more and more graphite into the hard carbon, eventually I see that above about 50%, you don't even notice that the hard carbon is in there anymore because you're still limited in your first charge Coulombic efficiency by the presence of the cathode material. On the other hand, by the time I get to 50% graphite content, I can now maintain very high capacity retention both during 4C and 6C fast charging without lithium plating on the surface. So here shows a comparison of the capacity fade during 4C or 6C fast charging. The black lines are the pure graphite. If I just blend 25% hard carbon into the graphite, I see that immediately I can see a huge jump in capacity retention. And we found an optimal blend ratio of about 50-50 to balance off the energy density and power density trade-offs. And once again, you can see the trends here. Pure graphite under fast charging, a lot of metallic plated lithium on the surface. Whereas by the time we get to 50-50 blend of graphite and hard carbon, we've pretty much eliminated that lithium plating, but still enable thick loadings and high energy densities. And this is an even simpler manufacturing solution. It doesn't even require that laser patterning. Just by simply changing the blends of the type of carbon, there's pathways to enable fast charge. So lastly, let me show you the one that was really the most exciting to us, which was thinking about the kinetics of the interface of the anode material. Most people, when they view fast charging limitations in batteries, are heavily focused on transport. They're trying to figure out, how do I get these lithium ions to go in and out very quickly? But there hasn't been nearly as much attention paid to the effect of the interface on the rate limitations of fast charging of batteries. If you go look in the battery literature, the only real reason a lithium-ion battery even works is because there's a magical surface layer that forms on the surface of the graphite during the first formation cycle. We call that the SEI, or solid electrolyte interphase layer. This is something we've known for many years. It's actually a quite complex composite material that has many different phases of organic and inorganic constituents. So we asked ourselves, okay, what is the ideal SEI layer and how might that influence fast charging? We thought really we'd like to make an SEI, if we're going to make an artificial one, as I'll show you in a moment with coatings, that's thin, conformal, pinhole free. It's got to have a high ionic conductivity for lithium to go in and out. It must be electronically insulating. And the key point is homogeneous. We'd like to get rid of all that heterogeneity of these different phases within the SEI. And by the way, it must also be stable at these very low voltages. And so we really looked to the literature of all the different coatings. Obviously, a lot of work has been done on coatings in lithium-ion batteries. Most of the coatings are on the cathode side of the battery. And one of the key enabling technologies, which we use as well, is atomic layer deposition, or ALD. You can see companies that are commercializing ALD coatings for enabling high voltage cathodes. Interestingly, there's actually a lot less work on this idea of artificial SEI coatings on the negative electrode or anode side. And most of what had been tested in the literature are these simple binary metal oxides like alumina, titania, that actually are pretty lousy lithium ion conductors. So the knowledge gap is here really, there's little to no work before this that focused on fast charging and rate capability by looking at coatings on the anode side. Luckily, we've been working on ALD of solid electrolyte materials for the last decade. A lot of that funded through our solid state battery research. We were trying to create optimal, stable, high conductivity interphases in batteries. And we stumbled on this really amazing material, which is a glassy blend of lithium borate and lithium carbonate. We call that LBCO. And we developed this ALD coating process for coating this LBCO that's very conformal. It's got the highest ionic conductivity of any solid electrolyte reported to date by ALD. It's chemically and electrochemically stable against lithium. So we thought, hey, why not try it? What happens if we coat this artificial SEI of this LBCO material onto the graphite? Again, we want to maintain compatibility with current lithium-ion manufacturing. So this is happening continuous after calendaring and drying of the electrode. We do electrode level coatings and assemble pouch cells in the battery lab. What we did was then we looked at that first formation cycle where the SEI layer is known to form. And if you zoom in on the voltage trace, there's this little bump that occurs at between 3 to 3.5 volts in the first formation cycle. This is the well-known signature of SEI formation. We were amazed to see that when we coated this ALD coating on the graphite, we were able to eliminate the SEI formation during the first formation cycle of the battery. Again, a lot of data here, and I'm a little short on time, so I'll go a little quick here. But long story short, the impedance of the interface becomes dramatically lower when you coat this ALD coating onto the surface of the graphite compared to the natural SEI, we call it, that forms from the decomposition of the electrolyte. So now we go to our 3 electrode cells and we see the control cell, we see the signature plating that I already showed. We're again able to eliminate that by doing this ALD coating on the graphite electrode, and that enables us to fast charge the battery without lithium plating, which was really a surprising find because most people would argue you have to solve the mass transport limit to enable fast charging. But here we showed just changing the interface enables fast charge. So very last, I want to give a little sneak preview here, if you allow me one more minute just on low temperature fast charging. It seems like now every February I get a call from the Associated Press of why are these Teslas not charging in Chicago in these cold days, and people are lining up and not able to charge their electric vehicle. We all know that when you go to very low temperatures, the charging time slows down, the EV performance decreases, the battery health is impacted. So there's kind of this, what we call a trilemma between fast charging and energy density I already talked about, as well as low temperature. And we have a paper that's accepted in the journal Joule that'll be coming out in a couple weeks. We're really excited about this. What we demonstrate is if we combine two of these ideas, the laser patterning plus the ALD surface modification, now not only can we do fast charging at room temperature without lithium plating, but look at these data. These data are showing, fast charging, or I'm sorry, even slow charging at a temperature of minus 10 degrees Celsius. What we see is even if you just do 1C charging here, the control electrode quickly fades. But if we look at the combination of the LBCO ALD coating and the whole, we're able to maintain greater than 97% capacity retention at a temperature of minus 10 degrees C. And note this is with no external heating, no thermal management of the battery. It means you could just cold charge the battery without plating. Not only that, we can do 4 to 6C fast charging at temperatures of minus 10 degrees Celsius without lithium plating, which is really unprecedented in the literature. And we can do this while maintaining thick electrodes without sacrificing energy density. And we show in that paper we can eliminate the lithium plating. So I'm out of time. I wanted to tell you a little bit about scalable manufacturing with ALD and laser. This is something we're also working on, high throughput, continuous roll-to-roll processing of both the coatings. So we've developed this mechatronic spatial ALD instrument that can print ALD onto the surfaces of electrodes. This is currently work that we're doing supported under an MTRAC project at Michigan. And we've actually developed a roll-to-roll laser patterning platform where we can rapidly scan and manufacture these patterned electrodes at high speeds. And I just want to point towards a startup company that spun out of our lab that is actually working on commercializing some of these technologies, Arbor Batteries. So if you're interested, get in touch with us. We're happy to chat and looking for industry collaborations there. So in summary, I showed you fast charging is possible without sacrificing energy density, that lithium plating is really this key bottleneck, and that's influenced by this spatial and temporal heterogeneity. I showed 3 complementary manufacturing techniques, and I showed if you start to combine multiple of these approaches, you could start to do truly remarkable things like 6C fast charging at low temperature without lithium plating. So with that, I'd like to thank all of the wonderful students and postdocs. They're the ones that really are in the lab doing all of this work. Our funding sources, as well as our collaborators, Jeff Sakamoto, Katsuo Thornton, and the students in my group that led this work earlier, Tay, Michael, Eric, and Yushin.